folks who said they wanted to talk about stuff. Let's hit Junjie, Rodrigo, I guess Wanchow as well because it's a D-tensor. Let's talk about perf. Is Junjie here?
Yeah. I'm here. I'm here.
Okay.
Yeah. So I don't know if one child here on the call.
Wanchow
Maybe
is here.
he's okay. Yeah.
Um,
Okay. Cool. Yeah. So basically, in the past, like 1 to 2 weeks, we're trying to see what like basically try to compare against the like D-tensor based tensor parallel with Megatron, and then to start this with, I created like a very simple MLP based benchmark uh, to compare what are the other gaps between Megatron version TP versus our D-tensor based TP. So and then we found that I mean a lot we already fixed something in the tensor side, but still we saw there are some like other CPU overhead when compared with Megatron. So maybe I can share my screen so that I can better uh, so for example, this is a MLP example. Basically two linear layers, and then this is like the like a complete traces for detensor based MLP example. So we can just start with forward. Um, to make it simpler. So for example, let's just look at the linear. So for example, if you look at the Eaton at mm. So the actual Eaton of here is pretty much here. Yeah, the actual Eaton of it of is here, and then as you can see that we have a lot of like a CPU overhead like here. So and then upon looking deeper into that, so because we are using tensor subclass, then we do a lot of a tree mapping to parsing the input argument. So that take some overhead here, and then yeah, I think so. You can ignore this functional collective for now. So, but this also called tree map only. Yeah, I guess that's the mainly thing we found. So yeah.
All right. NYC
Any
Dark
questions?
Ritual.
Is this the kind of things where we expect Brian's desugaring of subclass within Torch compile to remove?
yeah, I think this will completely remove overhead with torch
Okay.
compile. But the case is that without torch compile, when we run in a pure eager mode, this tree map stuff, because every Aton op we need to do this tree map stuff at least for some operations like say get the local tensor out of the tensor subclass thing. So it actually builds some incremental overhead over the time.
And how critical is the actual like what kind of perf gain are you looking for here for the eager side of things?
I think one good news for eager side is that when it comes to large language models, usually it's not CPU bound, and then FACP also have this kind of rate limit thing, so it kind of hide it. So for example, when we tested on a 13 billion llama model yesterday, we found that our TP is kind of like 70% of that like QPS versus to the Megatron one. So when it comes to large model, if it's not CPU bound, then yes, probably it's kind of okay. But if people want to use D-tensor or TP on like a more CPU bound model, then this is gonna hurt the perf. Yeah, like for example, for this small MLP model, I think based on the data from the trace, it's kind of like 7 times slower. Yeah, if you just count the number on the trace.
I would give you like two answers. One is, for anything that is small, eager mode is going to be very, very, very slow compared to what you could be doing. And that is true with or without the tensor. And, that's why torch compile is here. And so my second question would be, do you, or maybe not just for you, but for the whole room, like how much do we want to invest into perf for cases where we know eager mode is by design very limited and where torch compile should be quote unquote generally the right tool to use to get any kind of perf? Because even without the tensor, the general framework overhead of PyTorch is going to be slowing you down significantly here compared to if you were just doing the compute.
I think I'll answer that. I think we basically need to get closer. Maybe I'm not sure how close, but we need to get within maybe 5 or 10%, and we can use compile for like getting faster. But I don't think we can be 30% slower.
Sorry, Will, can you like elaborate some more why you think this?
Well, I just think that I made up the numbers, but I think that when you go between compile and eager, you need to be you can take some slowdown, but like if it's too big of a drop off, people would just find it unusable. And furthermore, I don't think we're at the point yet where everybody adopts compile. So I think if we were, that would sway me a little more. But there's still people who might like not be able to compile and want things to work fast.
One thing I would say, Will, is for example, if your network is like 4 element-wise ops, then compile will fuse that into a single kernel that does everything. It will literally be 4x faster. Like there are cases where we know compile will be orders of magnitude faster than eager. And you're saying this is not okay?
No, I don't think that's what I'm saying. The detensor overhead is it's additional overhead that's not even present in a normal model. So I don't think the overhead is okay. I mean, I don't think we have to compare eager to compile and say compile needs to be as slow as eager.
Yeah, this is especially this is especially true when it comes to tensor parallel. Like for example, currently if they just use Megatron, so I mean, although it's slow, but it's kind of like they already use it, right? Then if we want them to move to detensor, so one advantage is that our UX is better, so they don't need to write the like very hard coded that column wise, row wise linear stuff. But the thing is that if we kind of have a very bad performance here, then it's hard to like encourage people to migrate to our solution.
Okay. Sorry, NYC, did you want to pipe up?
Oh, no, sorry.
So okay, I'm gonna shift this conversation. Let's assume that okay, we do want to speed up detensor eager perf. So what approach are you thinking of doing for this? And I can give you some things, but you're not gonna like them. But like I know some ways you can definitely speed up perf.
I think Rodrigo also has some ideas. He was trying to like pre-compile the tree map stuff. Is Rodrigo on the call?
I'm not here.
No, okay.
So the current optimization we have is very simple. It's just that we cache the whole sharding propagation logic with some like say next iteration you're gonna be not running any of the sharding propagations, but still you will have this tree flatten and then some sort of hashing to get into the cache.
Right.
And yeah, so that's the current only optimization we're applying here.
Right. And then this trace is already where the caching working like properly. Yeah. If without caching, it even become even worse.
Okay.
And in general,
Go
I
ahead.
think yeah, I'm wondering like for the subclass perf optimization, is this the only way that like to further reduce CPU overhead? Like I guess there will be some tree map. Like, either we can move the tree map to C++, or we can, I'm not sure how that will help there, or we can like move the entire tensor subclass implementation to C++. But that will be a big effort, I feel. Yeah.
NYC.
I would challenge the fact that you must use TreeMap, by the way. TreeMap is just a convenient way to loop through the structure. If you know you're doing LMM, you know exactly what are the arguments, you can do whatever you need in 3 lines. It will be hard-coded, and you need to hard-code it for every op. So I'm not sure TreeMap is a necessary evil for you if you're really looking for performance.
But what do you guys think about the idea of caching tree maps? I mean, that seems like useful infra in general for PyTorch to have. We use tree maps all over the place, and I think for dtensor, we don't necessarily want to hard code because there might be a series of different ops used in a model, but it seems totally plausible to me that you'd only use like 5 or 10 ops in a model that go through dtensor, and then you'd be able to cache those efficiently.
Richard, are you here?
Yeah, what's up?
Can you tell us about the current state of TreeMap?
There's a OSS contributor who has a C++ implementation of TreeMap that he wants us to use. It is stuck somewhere at build issues, has not advanced from there. If you guys do want a fast C++ TreeMap, we can try to get it in faster. If you want to do caching, we can try that as well, but like it's kind of unclear to me what exactly you're caching here.
So when you guys said we were caching TreeMap, what I imagined in my head was something like your cache key is the operator, and then the cache basically just tells you where exactly to poke things out. Is that accurate or no?
Yeah, exactly. I think Rodrigo actually had a prototype where he essentially generated some Python code that would access the fields of the inputs in the right way, and you could just compile that code.
So some other things that let me think. So for dtensor, if I recall correctly, you guys need to interpose every operator. Is that right?
Yeah.
Yes.
Basically, every 8 op.
So there's some optimizations we can apply. We could have applied if you didn't need to interpose everything, but if you're interposing everything, then that's generally it. I don't know, like, do you even know if this is fast enough, even if you like literally do nothing besides go into Torch dispatch and then call into the function immediately after? Like, as in, like, the anti-pattern of performance optimization is you're like, I've got this thing and it's slow. Okay, how fast do you expect it to be, right? Like, we could be, for all I know, we're rearranging chairs on the deck when actually, like, no op torch dispatch is still too slow for whatever target you want.
Yeah, I think I asked Junji to do the baseline. I don't know if we did that yet, but we were going to find this out.
Yes, I was trying to do that yesterday, but somehow because sometimes we need to do some like resharding among when we do the sharding propagation. So if we only just call the function, those will lead to like
So
mm.
concretely, the way I would do this is I would run Megatron's TP, so you're not using d-tensors tensor parallel, but you're just like slowing it down by having the tensors being passed around be tensor subclass, a trivial tensor subclass.
Oh, I see. We can
That
do
lets you
that.
still do a realistic distributed setting. I mean, I don't even know if you need the realistic distributed setting, but if that's important to you because the workload matters, then you can do that.
Yeah, I think that this is a easier way to do that because to caching the detensor is make it super complicated. Yeah, I can do that. So and then we can see how slow that will be. Yeah.
Because if this experiment is too slow, then sorry guys, you gotta do it in C++. And we know that there is definitely a point where you do have to move stuff into C++. Like this is why all of PyTorch migrated into C++, right? And so if you're like, no, we don't want to move it into C++, then I'm not sure what to tell you. Like just torch compile it. Like another bullet for your gun is if torch compile can be made like fast enough to run on a per operator basis, you could just like have operator by operator torch compile pieces so that you like can zip through all the Python. It's kind of like the PyTorch caching, but you're caching the entire operator at that point.
Oh, you mean that like inside torch dispatch, we first do torch compile and then cache the small graph?
No, so you don't even do torch dispatch anymore. So like essentially when I call addmm on a d-tensor, it hits Dynamo's cache code entry.
I see. Does this mean we torch compile still on the whole model that is having d-tensor inside,
No, you
or
don't. The torch compile pieces are just the individual operator calls. So the model here is you're going to backend eager so that the warm-up time is quick, and you're basically banking on like you have a lot of Python overhead like PyTrees and torch dispatch redispatches, and the compiled code is going to be something like destructure the d-tensor, run an eager op, and then restructure the d-tensor. And the caching strategy is essentially for any unique set of arguments, modulo tensors and maybe integers if the dynamic shapes works out. I have a specific cache entry for that. This is not
I really
really
like
a
this
way we
idea.
use torch compile, but like in principle, this is possible to do.
The only thing that like sounds like it might be a deal breaker is if we couldn't like do we have a way to make it so that if we were to use torch compile in this manner and somebody else compiled their model outside, would they conflict, or would it be a graph break thing, or would the outer compile subsume the graphs from the inner compile somehow?
Generally, the outer compile subsumes the graphs on the inner.
Okay, that seems fine then.
Well, I
We
mean,
could probably
but
try
no one's
this.
ever tried this before. This is not really. You're sort of misusing torch compile in this regime, but it's also a possibility.
Well, I think we have a lot of options to try at this point, but agree that the first thing is to figure out if the baseline thing is good enough or if we're hopeless. So I don't think we should try prototyping like 10 optimizations. We should just try it to figure out if we can what the fastest we can be is.
Yeah, it makes sense. Yeah. I will first try that and then keep the team posted.
Any other comments? Okay. Otherwise, I want to move us along. Okay. Mark, tell us about what's going on with algorithmic efficiency. Just a quick update. No discussion unless people have questions.
All right, let me share my screen. Oh, actually, never mind. Yeah, so basically the ML, like there's a team at MLPerf doing like algorithmic efficiency, and they've been benchmarking PyTorch versus JAX. And they sent us like a post on Discuss saying that they just, with the perf they're getting, they just don't see any reason why anyone would submit a PyTorch model to the competition. So the reason that's the case is because like, there's 5 different models, and all of them are not torch compiling for some reason. So we've been working on reproing them. 4 out of those 5 models are still failing with like sec faults in data preprocessing. These are kind of all new issues for us since we don't really have data preprocessing in our benchmarks. Also, all of these pipelines are written using TensorFlow and like JAX, like data preprocessing libraries. So they're kind of like a bit janky once like Dynamo looks at them. There's a single model that where the data processing is working. However, like Dynamo thinks like a named tuple is a list. So I'm really hoping like Voz could help me figure out like what the heck's going on. So that's the most promising one. The others, we've opened issues, but for now, like I'm gonna try to debug this.
Any questions, comments? Okay. All right, more lightning updates. Will, tell us about data-dependent collectives.
Yeah, so
Oh,
Sorry, Will.
sorry, go ahead. Yeah, sorry, yeah. So I'm trying to add the all-to-all single operator, the functional collective version, and also make it supported in Inductor. Unfortunately, this operator is the output shape of it is dependent on the input data. Particularly, it has an operation where the first dimension of the output shape would be the sum of the something called output split slice, which is an input tensor. So which makes the auto single very different from the other collectives. So right now it seems that we need the symbolic shape support in inductor IR to be able to implement this operator. And I discussed with Ed yesterday, and seems it's something that we are planning to do, but will probably take us like some time to get there. So that's the current situation.
Is anyone here able to tell us the current state of like collectives in general in Inductor? Like this is just all working and there are no problems?
I don't know if I can say too much other than, for the most part, the few collectives we've added, like there's all reduce, reduce, scatter, all gather, and there's a couple flavors of them, and I think they're working okay. Yeah.
Okay, so
I've seen cases.
You're following how the existing collectives are implemented with this one. Is that right?
Yeah, that's right.
I've seen cases of numerical deviation in inductor that don't happen in eager for when doing FSDB. So I don't know if that's a bug in my tracing or if it's something that inductor introduces.
Well, it's kind of hard to believe that's from the collectives. I mean, either you're getting garbage memory, in which case I'd expect it to be a really big deviation, or they're working.
Yeah, it's strange. They're very small deviations.
It's probably something else from inductor, but not the collectives.
Maybe.
Will Feng, how blocked are you on this?
Like 100% block, I think. Well, I can special case such that like the split size is just none, like, and then I can like play with those use cases for now. But if to enable a general thing, we will need this symbolic shape in inductor IR working to be able to land this auto single operator. And auto single is actually being used by basically all the sparse arc in internal models. So yeah, we need this to be able to play with like tracing sparse arc, I think.
Yeah, I'm wondering if we have considered a different sort of operator signature for autowalls. Because I was looking at the how XLA implement their autowall. They basically don't require these data dependent shapes. And what they do there is that they will specify a split dimension, and they will specify a concat dimension. So basically, inside your operator signature, there's only two dimensions that is usually needed and don't need symbolic shape anyways. And what they are doing there is just like inside the operator, they will split the tensor, the single tensor, into multiple pieces and then do autowall. After they do autowall, they will reconcat the tensor in the end. That will make the autowall operator itself don't require symbolic shapes. But that will be a bit different signature than the current autowall single we have.
I wonder, can we have the same behavior? Because like split sizes is like a list of ints, like deciding how long each segment is. Like, will we be able to model the same using the XLA signature?
I think probably need some padding before like forming this original input tensor. Like the split size can be uneven split, right? But the if you specify only a split dimension there, probably you need to pad it evenly first, and then yeah, there's some slight difference there, but I would say this padding is anyway needed in all of other collectives. For example, all together, if your shard are different sizes, we'll need to pad it. So yeah, I feel it's kind of okay. But yeah, it requires some UX change from the user.
Well, I have a different question for you, which is, so you tried implementing it. I didn't look at your pull request, but for the inductor folks in the room, can you tell us exactly where it blows up, like based on your implementation?
So in all the other collectives, we try to compute the output size in the IR create method. So we basically want to specify the output tensor size upfront. I don't know what to put there, so then I just look around in the code base and be like, okay, let me put a SymPy symbol there, like
okay, so
unbound symbol.
So naively, so different question. Does your have you gotten it to work with backend eager? This collective.
Oh, you mean the functional collectives?
Yes.
With backend eager.
The alt wall.
Yes.
So it works with backend eager. Okay. So if it works in backend eager, then my expectation is that when you consult the meta val associated with the FX node you're lowering, it should say what its output size is, which is going to be an unbacked cement that you allocated in the meta function for your collective.
Yeah. That's a good point. I haven't seen like how to access the meta val from the IR create method.
Am I completely off base? Any of the folks who've worked on inductor here, does this make sense? Okay, we don't have the inductor crew here.
What's the question? Sorry.
The question is, apparently the pre-existing collectives in inductor are implemented by recomputing what the desired output size is. But this is confusing to me because whenever I'm lowering an A10 node, I should know what the output size is because I have a meta val property on the FX node.
I'm not sure. Yeah, I mean the size of why is recomputing the size undesirable
So
here?
recomputing the size here is undesirable because this is a dynamic shape. It's data dependent, and I mean we could reallocate an unbacked cement, but we should use the one that was allocated in the meta function when we were lowering to A10.
How would we even have a meta shape for something that's data dependent?
So when I have an operator that's data dependent, in the meta function, what I will do is I will call create unbacked cement, or whatever it's called in Richard's new version of the API, and I'll return that as the output.
I think it's probably recomputed because it hasn't like mattered up to this point if you're just recomputing known entities, but I'm sure you could use the it's being lowered from a big tensor from a node that has the meta valve. I'm sure we could reuse it.
So Will, just to confirm, in the lowering code, you do have access to the FX node. Is that right?
You mean like lowering .py where I call the IR create?
Yeah, you should have. There's you because you're lowering a FX node that corresponds to the functional collective.
I'm looking at the lowering code for the existing functional collectives now, and the input signatures to these things don't contain the output tensor. That's part of maybe that's part of the problem.
But it is accessible. It's just like those are the inputs are the like transformed like inductor IR from what the inputs would be. But the output shape is accessible. I can fall offline.
Okay, so Elias, can you help Will? I feel like we just have to change the call side or something so that it passes in a little more info. Because Will, I was telling you that inductor dynamic shapes doesn't work, but it like doesn't work in a very it's very, the delta is very small actually. Like the patch I showed you, right? The most important thing is inductor doesn't know that it needs to bind unbacked cements when it's generating the code, and that's like a 2-line change, which I haven't landed yet because it's a very hacky 2-line change, but that's good enough to get pointwise and reductions going.
Thanks a lot. So does it mean for size hint we need to get the right size hint instead of I don't know, like I'm wondering, even I get the size symbol from the meta val, is there something else in inductor that we will need to get done to get it working?
Yeah, so the general recipe in the rest of inductor is you are not allowed to call size hint. Okay? And how exactly, so obviously inductor does call size hint a bunch. So what exactly do you do in this situation? Well, there are a few options, right? One is that, we were using the size hint because we wanted to apply some heuristic for whether or not to do something or not. So in those cases, you can just change the size hint call into a is there a size hint? And if there's not a size hint, you just choose not to do the optimization, which was optional anyway. In some cases, there is some code where you have to know exactly what the size is to do something, and that's a hard blocker. But I know that for pointwise and for reduction, this never happens. And I don't know how long the unbacked cement lives, but like you only really need to get through all the way to at the point where you like pull it away or something like that. So like there's typically a limited extent that needs to work with the unbacked cement.
Got it. Yep. Makes sense. Yep.
And yeah, so there's a bunch of places that I know you need to handle, and that's in the diff that I sent you. And like it's working for pointwise and reduction, which is basically most of the important stuff in inductor.
Yep, sounds great. Thanks.
Okay, so I threatened to use up the rest of this time for my stuff. So I'm going to talk about some new developments for unbacked cements in dynamic shapes. So this is called expect true. I'm going to share my screen. Just a sec. All right, here we go. So so we were just talking about unbacked cements. So unbacked cements are very annoying to deal with because our tracing system in PyTorch is predicated on the idea that whenever I do a conditional, I can just guard on it and resolve the conditional using the real values in question. So unbacked cements, you can't do that because you have no idea what the value is. And so if you are doing some sort of enablement, so the thing I was looking at earlier this week was this example of a split. So what am I doing here? I have a lengths tensor. It's just an int tensor which contains how long various subtensors are. I read out all the values. Actually, let's do the dynamo test because it's better. So I read out what the values of this tensor are, and then I do a little, say, oh, well, they're all sizey things, and then I split on these sizes. This is exactly what happens in key jagged tensor in TorchRec. So this didn't work. And what happens is because all of these sizes are unbacked cements, so we end up doing tons of conditional tests inside of split, because we were doing things like, oh yeah, the sum of the lengths has to equal the size of values, and oh yeah, I'm doing successive narrows to get out the chunky tensors, and all of those narrows have to be in bounds. So you generally just end up with a bunch of like failures where it's like trying to guard on data dependent value. So expect true is a trick that we can use to eliminate a large portion of the sort of nudging of our system. It uses the observation that if I do a conditional on an unbacked cement, but I would error if that conditional result false, like I'm just doing error checking if things are in bounds, then for the purposes of unbacked cement reasoning, I can simply assume that it is always true. Because if it was false, I'll raise an error. And to make sure I actually raise an error if the condition is not satisfied, I just push this to runtime. I can just say, okay, well at runtime, I will assert that this is greater than or equal to 0. And while I'm compiling, I'll just assume that it's greater than or equal to 0 because I wouldn't be able to compile it anyway if it didn't match. So how exactly does this work? So there's a new function called expect true. And what it does is if you have some unbacked cement, you can do some condition on it, and you can say expect true on that cement, and this will work. And you will get back true in this case, saying that, yeah, okay, I'm assuming that it's true. And this will generate a deferred runtime assert that you will plan to run later, either in, if you're exporting your program, this will show up in your export. If it's inductor should generate these runtime tests. And you now can always, do guards on this later. Yes, Will?
Confused how this actually makes any difference to the status quo, because it sounds like you're still paying the cost of doing the runtime check, which is essentially doing a guard, isn't it?
So the distinction between guards and runtime tests is that guards can always be executed at the beginning of a compiled region. So a guard is allowed to fail, and when a guard fails, that doesn't mean there's an error state in our system. It simply means the compiled code is not eligible to be run. So a runtime assert on a unbacked cement is different because you can't run it ahead of time because you have no idea what that unbacked cement is at the beginning, right? There was going to be some non-zero call or some item call that actually told you what the value is. So you can't guard on it up front. Instead, you can only be like halfway through executing, at which point the assertion fails.
Okay, I missed that this was unbacked, so that makes sense.
Let me see. Yeah, so you can't use expect true if you actually legitimately need to condition between two branches, because all expect true does is says, no, we're always taking the true path. Don't worry about the false path because it errors. I called it expect true because that there's this concept in GCC and Clang called built-in expect, which basically says, hey, this variable is probably true. Please generate code accordingly. So I figured this was a nice analogy to that case. Yes, Animesh.
So here we are not reducing the number of cards, right? The number of cards are still same, or like the number of checks are still same. We are just postponing them to runtime.
Yes. So whenever you expect true to discharge to basically make one of these tests on booleans go through, you don't run it in guards, but you do run it at runtime.
So one of the problem that we saw with key jagged tensor is like just large number of these checks. So we will still have the same large number of those checks.
That's right. But what I
Okay.
guess is the hope is that if we beef up the symbolic reasoning enough, you'll end up, being like, actually, these 50 checks, actually, you can just do one check, and that check implies all of them.
I see.
Well,
Can people like use / abuse this to delay some guard overhead by using this on backed Simmons and then having it so that the check happens kind of like in parallel to other computations? Is that how this thing would be implemented, or is this just not allowed?
No, you're right. You could potentially use this for backed Simmons. And yes, so the model here is that you only want to do critical path guards in the code cache selection, and then once you start being able to execute kernels, you can do the rest of the error checking to make sure you aren't going to hit an error case. So yes, I did not implement this, but this is potentially something you could do.
Okay.
And just to show that this works, so with this change, you can successfully torch split. You do need to say that everything you're passing in is something like a size. That's what's going on with the constraint as size here. I did have to make some slight modifications to code. This is very similar to the unbacked cement stuff we talked about in February. So let's just look at one particular example. So in the old code for narrow, there's this test to see if start is not equal to cur size. If start is not equal to cur size, then we call maybe wrap dim on start cur size. And what this essentially does is it says, hey, start says, where you want to start the narrowed view of the tensor in question, and the valid values for this are negative cur size. Cur size is the size of the dimension you're narrowing. It can either be negative cur size, which is doing the good old-fashioned Python negative indexing semantics, all the way up to cur size. But the old implementation did this a little strange. It used maybe wrap dim, which normally is used for dims, not for sizes. It was like being abusively used in this case. So maybe wrap dim says that the valid range is to cur size -1. But it turns out if you're doing a narrow, you can also narrow all the way to the end, right? That just says you're going to end up with an empty tensor in this case. So they just said, okay, well, I'll wrap, but only if start is not cur size. If it is, I'll do nothing because that's just valid. This is a very strange way to do it. And I rewrote the code to be much more natural, which simply says that, hey, start has to be greater than or equal to negative cur size and less than or equal to cur size. And I'm using this special expect true here, essentially to say, hey, this is always true. You don't have to worry about it. And so when I rewrite it in this way, there's no longer this not very nice conditional on an unbacked cement. There is a nice expect true, irrefutable guard, and we successfully get through. I do still need to deal with negative starts, but in fact, in this use case, I know that all of my lengths are greater than 0, so we actually are able to discharge this conditional even though start is an unbacked cement. Similarly, there's a check that the narrow range is in bounds, and this one is just marked as a torch sim check, which just says, hey, I take a sim bool and I'm going to assume this is true. And what else? Oh, and I also, in Python, it's very easy to do this because everything is overloaded. So I just inserted inside the implementation of check that we just expect true cond in this case. Did I have to make any other changes? There's like 2 more changes I had to do. So here we previously tested if start val is greater than or equal to. So this turns into a greater than test. And the idea here is that I typically know that my length is in bound for the tensor I am slicing into, and that includes being at the very end. So if I change this condition to say start val is out of bounds and only then do I clamp it to sizes dim, then I statically know what the result for this case is. And here I just replaced a if blah raise with use of the check macro in this case. There's just one little extra thing I have to do here, which is I have to say, hey, this is not statically obvious, even though actually it is always true and split with sizes. So I help the reasoning system out by just saying, hey, this is true. You actually don't have to test this, but I tested anyway for ease of reasoning. And that was all I needed to get split working. Questions, comments? Yes, Animesh.
So these are not guards anymore, right? They're not run through check FN. So then who is responsible for running these? Like, do we have to make these changes like expect true in the code itself so that they run at runtime?
Good question. So the semantics of check haven't changed. So if you don't have unbacked Simmons in the expression, it turns into a normal guard. So the special deferring to runtime only happens if there are unbacked Simmons. So like if you like forget about the stuff about unbacked Simmons, it seems clear that the before and after here are the same. And I've just sort of like spruced things up a little with our helper function. Any more questions, comments? So last time I went and did a bunch of stuff like this, Horace, who is not here right now, like basically I did this a lot more aggressively for contiguity testing, and Horace talked me out of it, and we did unsound 0-1 specialization. So this situation kind of smells similar, where I am making a bunch of subtle changes to error checking again to like make unbacked Simmons go through. So you could be worried maybe this is also too much. For this particular case, it seemed okay. Like all of the changes seemed very reasonable to me, and not difficult to explain why you should do it this way and not some other way. It's possible that for more complicated examples, we will get into trouble, but I'm not. I'm optimistic. It seemed to work, and the rest of what I need to do is like shove these at embedding bags, which should be easy. So I'm well, no one has reviewed the second PR yet, but I'm hoping you will agree with me and stamp yes on this PR. We don't have very many expert people in the room, but this should also greatly improve user experience exporting models with dynamic output sizes. Okay. Any more comments, questions, last minute shout outs? All right. We'll go ahead and end early. Thanks, everyone. See you next week.
Thank you.